This video will be on section 4.5, absolute extrema. The two topics in here are really just dealing with absolute extrema. We'll see what it means in a second. The first one is absolute extrema on a closed interval. Now, I may have said this word before, but a closed interval is just an interval that has brackets on both endpoints. So I'll write an example, but first I'll write in words. A closed interval has brackets on both endpoints, meaning we're including both the endpoints. Something like 1 to 7, both with brackets, is a closed interval. And then anything that doesn't have both brackets, it can be one parentheses or both, that it's just what we call a not closed interval. So it's a little easier to do absolute extrema on a closed interval, as we'll see. And then we'll talk about how to do it on a not closed interval. And all this means is that at least one of the endpoints is a parentheses. So at least one of the endpoints is not included. And so one with something like 1, 7, but one has a parenthesis. The 1 can have the bracket, the 7 can have the parentheses. Or if they both have parentheses, all the same, they're all not closed. All right, so what is absolute extrema? The formal definition, it doesn't sound very useful, but I'm going to read it off and then I'll explain how it's very much related to what we've been doing in this chapter. So it says let y equal f of x be the graph of a function, then the absolute maximum of f is some number f of c, such that f of c is greater than or equal to f of x for all x in the domain of f. Now, what does this mean in words? Because that's an awful heavy math. Well, the f of x, the f of c are the y value outputs of the function. So really it's telling you that the absolute maximum is the largest y value the function spits out. Okay, and then the absolute minimum is the same thing, but the smallest. So the absolute minimum of f is some number f of b, such that f of b is less than or equal to f of x for all x in the domain of f. So that the absolute minimum is the smallest y value. Right. So the absolute maximum and minimum, what we'll do is work an example, and then I'll show you on a graph, what really we're looking at and how it actually corresponds or is a little different. So they're calling maximum and minimum because they're similar to the local maximums and minimums that we've done before, but the absolute maximum minimums have a slightly different meaning. All right, so this first one doesn't use any calculus at all. It gives you the graph of this function in the homework, so I'll graph it on the calculator. And it says, by inspecting the graph of the function, find the absolute maximum and absolute minimum of the function h of x equals x squared plus 2 on the interval -5 to 2. Now I'll go ahead and repeat once again that the fact that this is a closed interval, both brackets, is important. When we look at our example, it'll make more sense. I'll be able to explain better when we have the picture. But I'm going to go ahead and graph this function, and I'm only going to look at it on this interval of x values. Okay, so y equals x squared plus 2 is the graph we're looking at. Now the window, the x values are only ranging from -5 to 2. So the reason I'm going to make them exactly that and not make it a little bit bigger is I don't want to look at anything outside of it. So just -5 to 2. The y values on this range, like I said, the graph is given to you, but this is like the graph of y equals x squared shifted up to, so it's like that parabola gone up to. If we make our y minimum 0, we'll get to see the bottom. And then the biggest it gets, I'll just make 30 the biggest for reasons that I'll be able to explain after we do the problem. Right, but this will give us a good picture of the graph. Right, so once again, this is the graph of y equals x squared plus 2 on the interval -5 to 2. I don't want to see anything else outside of it. Right, so the absolute maximum, use different color. They don't need the hyphen there, but the absolute maximum is the largest y value, meaning the highest the graph goes. And if you look at our picture here, the highest the graph goes is definitely on the left side, all the way left at -5, the smallest y value or smallest x value. But we want the y value. We don't really care about the x value. So if I hit second calc and then value, and I plug in x equals -5, it'll tell me the y value up there. You could have also plugged it in yourself and done that out. But y equals 27 is the absolute maximum on this interval. And then the absolute minimum is the lowest the graph is. And what's the y value, the lowest this graph goes? Well, we can see the lowest the graph goes is down here. Since this is a parabola, we know this is called the vertex of the parabola, but it's occurring at x equals 0. So if we hit second calc and plug in 0 for x, we get the lowest y value, which is 2. Also, you could have done that part by hand again. Just plug in x equals 2 to our formula. Sorry, x equals 0. All right, so one thing that I want to go ahead and mention is why the brackets are important. Why do these need to be included? Well, if we didn't actually include -5, what would happen is we could plug in every single number that's close to -5, like -4.9, -4.999, and so on, but we could never actually plug in -5. So there wouldn't actually be an absolute maximum because we could always plug in -4.9, always add in another 9 at the end of the decimal point and make it bigger. So that's why it's needed. If you don't include both of your endpoints, then if you're using one of them to find the absolute maximum or minimum, what's going to happen is you're not actually going to have it. So the endpoints, the brackets being included is very important. Right, now the absolute minimum here, shifted over here, this occurred at the vertex of the parabola, but we know that this is also called the local minimum because it's the lowest the graph goes around here. And we figured out how to find the local minimums before. That's what section 4.1 is all about. Right? We figured out the local minimums by finding the critical values, making a sign chart, and then going through the process. Right? But one thing that we'll see in this section is when you find absolute maximum and minimums, it's a little bit easier. You don't have to make a sign chart that we will see. Right? But the culmination of what's going to happen here, what this picture is really trying to tell us is if we want to find absolute maximum and minimums, we have to check these different values. we have to check the endpoints, because the absolute maximum, as we saw here, occurred at the left endpoint. If we move the interval over, maybe it would occur at the right endpoint. So for our example here, what we'd have to do is plug in -5 and 2. Now the calculus part, if we wanted to find that absolute minimum that occurred here, that one was at a critical value. It's the bottom of the graph. The tangent line is horizontal. However you want to think about it, that is occurring at a critical value. So we must find and plug in critical values. Critical, I added an extra I in there. Right, but really what's going to boil down, at least in the first part of the section, when you're given a closed interval, you plug these in, you find your critical values of your function and you plug that in. The largest number you get out is your absolute maximum. The smallest number is your absolute minimum. Right, and that's pretty much what this theorem says. It can be a little more confusing in words. That's why I wanted to do that example out. But it says, suppose f is a differentiable function on the closed interval a comma b, right? Both brackets, both included, a and b are just numbers. Then the absolute maximum and minimum value of f on a comma b exists, right? Once again, if you don't have double brackets here, you might not have both. You might only have one, or you might have neither. And they must occur at either the endpoints, so a or b, like we mentioned above, or any critical numbers of f between a and b. All right, so this is telling you exactly what to do, what we outlined up here in our picture. For these problems, we're going to plug in our endpoints, find the critical values, plug those in, and see which one is biggest and smallest. All right, so the first one here, it says, find the absolute maximum and minimum values of the function f of x equals 3x plus 6 on the interval 0 to 9. All right, so the first thing, as soon as you see this absolute word, before in 4.1 we were doing local minimums and maximums. When we do absolute maximums and minimums, we want to plug in the endpoints. I actually do that first before I worry about the critical numbers, but you can do it in either order. I just find that if you do the critical numbers first, that's easiest to forget about this part. So we got to plug in 0 to our original interval, or our original function, and we got to plug in 9 to our original function and get both those numbers out. So the first one here, 3 times 0 is 0, plus 6 is 6, and 3 times 9 is 27, plus 6 is 33. Now, you don't want to make any choices here. This one might be the absolute minimum, this one might be the absolute maximum, but we don't know yet because we need to find critical values. Right, and we know how to find the critical values from before as we find the derivative. The derivative of this function is very short, it's just 3. Then we set it equal to 0 and solve it. But 3 does not equal 0, so there are no critical values. Right? There are no critical values, which means these are the only two choices we have to find the absolute maximum minimum. 33 is the bigger one, so this is the absolute maximum. And 6 is the smaller one, so this is the absolute minimum. Now, if you think about what this graph looks like, this is the graph of a line. A line is either going to go up or down in a straight line, but it's never going to turn and have a maximum or minimum, a local one. So this actually makes a lot of sense. For our answers, the way the homework might want it might just want the y values here. It might ask for the ordered pair or the wording. So the wording here would be, there is an absolute maximum of 33 at x equals 9, and there is an absolute minimum of 6 at x equals 0. All right, or if they ask for ordered pairs, we would have 9, 33 and 0, 6. Right, but this one, is a good example to see because not every function that, like we've seen before, has critical numbers. All right, number 2, same idea. We want to find the absolute maximum and minimum values of this function. This time we have f of x equals 4x squared minus 8x plus 1 on the interval -3 to 3. All right, once again, plug in those endpoints first. If we plug in the endpoints, we plug in -3 to our original function and 3 to the original function. We have 4 times -3 squared minus 8 times -3 minus 1. And what is that? Let's go ahead and do it on our calculator, so just to be careful. And we get 59. And if we plug in 3, we get 11. I guess I should write out the visual here. We plug in 3, we get 11. But just because last time there wasn't critical values doesn't mean this one will work, or doesn't mean this one won't. So we got to find the critical values now. All right, so we've got to do the derivative. The derivative of our function, the derivative of 4x squared is 8x. The derivative of 8x is just 8. The derivative of 1 is 0. We got the derivative computed there, and now we set it equal to 0 and solve. So to solve this, we add 8 to each side. We got 8x equals 8, and then we divide by 8, and we get x equals 1. Now here's something important. This one we do plug in because it is between the interval -3 and 3. If we got 4, for example, we wouldn't plug it in because it's not inside the interval. So I'll just write a little comment here on the side. If critical value not in the interval you're given, so in this example, -3 to 3, like x equals 4, don't plug it in. Because it's not inside the interval. So think about if we graph this from -3 to 3, what's happening at x equals 4 is not in our picture, or we don't want to use it at all. But we do have to plug in 1, as we saw. Plug it into the original. We got to plug in 1 for f of x, for x, and f of x we get 4 times 1 squared minus 8 times 1 plus 1. And then here Since this is just 1, it's not too bad. 4 times 1 is 4, minus 8 plus 1, which is -3. And now this is one where at least, you have to use something else. The largest value we see is the 59, so this is the absolute max. And -3 of the 3 values we have to plug in is the smallest, so this is the absolute min. And once again, we can put it in words just like from before. Let me leave it on my screen. We could say the absolute maximum occurs, or the absolute maximum is 59 at x equals -3. And the absolute minimum is -3 at x equals 1. Once again, if you change the interval, I think there's one homework problem where it gives you the same function in 2 different intervals. It can change your answers, so just be careful with that. Right, now what do we do if it's not on a closed interval? But this is not an uncommon thing. It's when it comes to word problems. Typically your domain, it will start, if it's referencing time or sales of some product, the amount of product, it will start at 0, which may be included or not included, but it might go on forever. So 0 to infinity or 0 to infinity with double parentheses, or negative infinity to infinity. How do we figure out the absolute maximums and minimums? Well, this is actually kind of a question that we answered before. When the intervals are not closed, we will have to find the critical values and make a sign chart to see what is happening for those. Okay, so this is why closed intervals are so great, is you don't have to do the sign chart. If there is not a closed interval, we're going to make a sign chart like 4.1. All right, so number 1 here says find the absolute maximum and minimum if either exist for f of x equals x squared minus 14x plus 4. Now the reason it says if it exists is we're not given a closed interval. It's actually understood if you're not given the interval that it's on its domain, and this thing has domain negative infinity to infinity. Right, if you are still given a domain, which I believe in the next one we will be, use that. But this one we aren't given a domain, so we have to use negative infinity to infinity. Now the reason it says if either exists is because the interval is not closed. If the interval is not closed, then you might have only one or you might have neither. Right. So what do we want to do? Once again, if you read up here, we find the critical values and then make a sign chart. Right, so the derivative f of x, derivative of x squared is 2x. The derivative of 14x is 14. The derivative of 4 is 0. We set that equal to and solve it. Set that equal to 0 and solve it. We get 2x equals 14. And then we divide each side by the 2. And we get x equals 7. Right. Now, because the domain is negative infinity to infinity, this is automatically a critical value, and it's our only critical value. Right, so what we'll do is we'll use this when we make our sign chart. And remember, what we do with the sign chart is we plug in a number on each side to the derivative and figure out when it's increasing and decreasing. So to the left of 7, I'm going to plug in 0. To the right of 7, I'm going to plug in 8. And make sure you plug into the derivative. All right, so f prime of 0. What do we get if we plug in 0 to the derivative? Our derivative formula is 2x minus 14. So that's negative 14. Because the derivative is negative, it is decreasing over here. And I can draw my downward arrow like that. If we plug in 8, for x, we got 2 times 8, which is 16, minus 14, which is 2. And that is positive. Positive derivative means it's increasing. So it's going back up. All right, so what's happening with the graph here, especially if we don't have the graph, if we don't have any type of calculator to graph it, what this is telling us is it's going to be decreasing from negative infinity all the way till we get to 7, and then it's going to start increasing from 7 to infinity. So what's happening here is 7, we know it's a minimum because it's the way we did our sign charts before, but it's an absolute minimum. Okay, now if we had another critical value, let's say over here at -5 or something, and it was increasing, so it goes up, then down, then back up, then this wouldn't be an absolute minimum because it would be below it over here. But as far as the graph of this, you can graph in your calculator and see that. Or if you know that this is actually a parabola, then the vertex is the absolute minimum. So that checks out with what we're doing here. Because it's a parabola that opens up. Right. So back in college algebra, when you're talking about the vertex of a parabola and stuff, you didn't use the term, probably didn't use the term absolute minimum. You probably just used the word minimum. But another thing here is that there is no absolute maximum because it's going to go up forever. Right? And we don't use infinity or negative infinity to reference an absolute maximum or a minimum value because it's not a real number. So there's no absolute maximum, but there is an absolute minimum. It's at x equals 7. And then the y value, we would plug in 7 to the original function. Right, so make sure we plug in 7 to the original function. And we get 7 squared minus 14 times 7 plus 4, negative 45. Right, but that is the main difference. If you do not have a closed interval, you have to make a sign chart. Right, you can't use any shortcuts, unfortunately. Yeah. All right, so number two would be what we call kind of like a half interval. It's stopping on one side, 0, and then going to infinity. But I like to call them half intervals if one's a bracket and one's a parentheses. So this one says find the absolute minimum. Notice it doesn't say absolute maximum and minimum. So we're probably going to have an absolute minimum, and it's telling you to find it on the given interval 0 to infinity for the function f of x equals 2x squared minus 16x plus 3. Right. Now, once again, what we want to do is exactly from before. Find the critical values because it's not open. Or sorry, it's not closed. Okay, we find the critical values. Let's do that. Do the derivative. The derivative of our function here, derivative of 2x squared is 4x. The derivative of 16x is 16. We set that equal to 0 and solve it. And we do that, we add 16 to each side, we get 4x equals 16. And then divide by 4, we get x equals 4. Now, because we don't have our interval being in negative infinity to infinity, you do have to make sure this is inside the interval. Because if it's not, then it's not helpful. But 4 is between 0 and infinity. So what we're going to do is make our sign chart and mark this off. Okay, so there's my number line. The only number of interest here, the only critical value is 4. But one thing you have to make sure of for this one, you can plug in any number to the right of 4 because it can go to infinity, which I'll just plug in 5. But you can't plug in any number to the left because we're not allowed to use them all. We have to use only from 0 to infinity. What I like to do for these is just draw a bracket. And I just say don't go behind here. And plug in something in between, like 3. So let me use same color like I've been doing. So we're going to plug 3 and 5 into our derivative. Because we want to know if it's increasing or decreasing, what is it doing? Right, so we do that f prime of 3. The derivative equation is 4x minus 16, so we get 4 times 3 minus 16. 4 times 3 is 12, minus 16 is negative 4. So it's decreasing, which means it's going down between 0 to 4. Right, and then if we plug in 5, we get 4 times 5 minus 16. 4 times 5 is 20, minus 16 is 4. So positive means it's increasing, and it's going up after 4. Right, so what is our absolute maximum? Or sorry, absolute minimum? We don't need to find the maximum. Well, we don't really care what's going on behind 0. The way our picture is drawn, the fact that the only critical value is 4, means it's probably decreasing from negative infinity all the way to 4. But that doesn't really matter for this problem. It's decreasing starting at 0 till we get to 4, and then it's going to shoot back up forever. So it's going to look something like this. Our graph looks something like this, and the 4 here is not only just a local minimum, it's an absolute minimum again. Right? And we don't care about this one not having an absolute maximum. It wouldn't, because it goes up to infinity. There's nothing stopping us from going that way. We can't go up this way because we have to stop at 0, but we can go all the way to the right. But there is no absolute maximum for this problem. The absolute minimum, there's an absolute minimum at x equals 4, and then the y value, we plug it into the original. Right, we plug it into the original because it's actually on the graph. So 2 times 4 squared minus 16 times 4 plus 3. And if we do that, 2 times 4 squared minus 16 times 4 plus 3, we get negative 29. So there's an absolute minimum at x equals 4 of y equals negative 29. Right, now this is more for the next section, but I'll just preview it in here. The last two examples are more like how word problems work. You're not going to have a closed interval, you're going to have an open interval. But what you'll notice about each of these is that they both had one critical value. If you only have one critical value, then you're guaranteed that that critical value is either an absolute maximum or minimum. You just have to look at the sign chart to see which one it is. Both of ours just happen to be minimums, but that's something to keep in mind. So I'll just write a little note here, because this is the way most word problems work. If there is only one critical value, then there is an absolute maximum or minimum, whichever one it is, at that critical value. Now, the one assumption here is that for the function, the domain of the function is negative infinity to infinity, but that's such a common occurrence, especially with word problems, the equations you get out, that you probably won't run into a single one that doesn't have the domain negative infinity to infinity. But I just like to bring that up now because when we get to the next section, it saves a lot of time if we realize there's only one critical value. If there's only one critical value, it's going to take care of the rest for us. But that is our section on absolute extrema.